So once again, you can download the notes from Schoology or take your own. I would suggest as a subject for this set of notes that you go ahead and do atoms, molecules, and ions, or atomic basics. All right, well, we're going to start with a little bit of history. The idea of the atom goes back to ancient times. If you look at Western materials, you'll find that the earliest reference to the atom came from this guy, a Greek philosopher by the name of Democritus. And Democritus was around several hundred years BCE. He was a philosopher, so he didn't actually do any experiments. By observing the world around him and just thinking, he came up with the idea that matter could be cut over and over and over and over again into smaller and smaller pieces. But eventually you would get to a piece that was so small that if you cut it any further, it would no longer be the same material. And that smallest piece, or small particle that he came up with, he referred to as the atomos, which meant the uncuttable. Okay? If you look in Eastern literature, you will find this guy come up, Acharya Kanada, and he is another father of atomic theory. And basically, he came up with the same idea as Democritus did, but he was in India instead of in Greece. So again, just different parts of the world, similar ideas arising in the same times. But neither of these folks, again, were scientists, so there wasn't any evidence to support their claims at all other than rational thought. Okay. However, atomos is, of course, where we get our modern word atom. So then we fast forward about 2,000 years to the early 1800s and the British scientist John Dalton. John Dalton basically was studying matter again, and he was relying on the experiments of some other people, some experiments he was doing himself, as well as his reading of classical literature such as ancient Greek philosophers like Democritus. And from that information, he came up with what was basically the first modern theory of the atom. And he is basically known as the father of chemistry because of this. And so his idea about atoms has 4 main ideas. The first one is that each element that exists is composed of extremely small particles called atoms. So he kept that name from Democritus, etc. But essentially, if you have an element of a substance and you break that down into its smallest units, you have an atom. So all matter is made of small particles. The second part of his atomic theory was that all atoms of a given element are identical, and atoms of different elements are different, which doesn't sound like rocket science now, but it was sort of at the time. So if I have an oxygen atom, it's the same as any other oxygen atom. If I have a carbon atom, it's the same as any other carbon atom. But an oxygen atom and a carbon atom are not the same. The third one, it was something that came from another scientist by the name of Lavoisier, which was this idea that atoms are neither created nor destroyed in chemical reactions. So they are not changed from one element to another. They are fundamental, and they're neither created nor destroyed. And last but not least, Dalton's last thing basically said that you can take atoms and you can combine them together. And when you do that, you get a compound. And in compounds, any particular compound has the same relative number and kinds of atoms. So the kinds of atoms are the same, and the ratio of the number of those atoms in a particular compound are the same. Mm-hmm. So as I said, this was the first modern idea about atoms because it came from John Dalton's scientific observations that he made himself and the scientific ideas of other scientists like Lavoisier, who gave us the law of conservation matter, and Proust, who gave us the law of definite proportions. These 2 laws will actually come back up in more detail in a future unit, and we'll actually do a lab that has to do with those. So Dalton's ideas, which were published in 1806, carry us pretty much all the way through the 1800s. in that time, we see an explosion of chemistry, people formulating new compounds, the discovery of new elements, etc. And so the 1800s is a very, very busy time for describing and finding new compounds. Toward the end of the 1800s, though, in 1897, we start to get some new information about atoms. Okay, so at this time, a scientist by the name of J.J. Thomson is doing experiments with something called a cathode ray, which essentially means that you have electricity passing through some metal plates in a glass tube that is evacuated except for some kind of inert gas, some gas that doesn't react. And as you do this, what you basically get is you get these green or purple rays that go through the glass tube. So what he finds then, that there are streams of negatively charged particles with mass coming from cathode ray tubes causing fluorescence. So a couple things here. First thing experiment he does is he puts a little wheel inside one of these glass tubes, and what he discovers is as these rays are going through, it actually causes this wheel to spin, which tells him that whatever's going through there is more like particles, bits of matter, than it is like light. If I were to shine a light on this wheel, it wouldn't spin. So he knew then that even though they were giving off light, the beam was actually made of little tiny particles. The second thing that he did is he put another electric field around this with positive and negative, and he found that as he ran the cathode tube toward that, it would bend away from negative and toward positive. Now he knew opposites attract and like charges repel, so that told him that these particles were negative. So he knows that they have mass, and he knows that they're negatively charged. He confirms the negativity by looking at this and putting a magnet by it. And it was well known by that point in time that negative particles would be deflected by a magnet. Finally, Thomson went ahead and he did these experiments by changing and putting different metals in and different gases into these tubes. And what he found was no matter what he made the ends out of in terms of metals, and no matter what gas he put inside, he always got these cathode rays. So this led him to believe, again, that there was a negatively charged particles that have mass inside these materials. And so he figured they must be inside the atom. Thomson's final experiments basically were allowed him to be able to figure out the charge to mass ratio of the electron based on how much deflection there was when he added different electrical current to the charged plates that were inside. Once Thomson did this and was able to figure out the charge to mass ratio, at that point it was figured out that all you needed to do is figure out the charge or the mass of an electron, and you could figure out the other thing. And that happened in 1909 in Chicago by a scientist by the name of Robert Millikan. Basically, what Millikan did is he put tiny little oil drops into an apparatus that he devised himself. And it would cause, there was a tiny hole in a metal plate that would cause oil drops to fall down one at a time. And that hole was in a plate that ended up being positively charged, and he had another negatively charged thing on the bottom. And by submitting the oil drops to a source of X-rays, basically what he was doing is he could go ahead and add electrons to the outside of the oil drops. And then what he would do is he would take these electrically charged plates and he could get it so that one of these oil drops would basically be repelled by the negative and attracted to the positive. And if he could go ahead and balance that out with the force of gravity pulling down on it. And with all of that data together, what he was able to figure out was that the drops always required a charge that was some multiple of the same number. That number ended up being the charge of the electron. So it always took 1.602 times 10 to the negative 19th coulombs per electron to make it float. And with that, then we were able to figure out the mass of the electron as well. So with that information then, we end up with what's known as the plum pudding model of the atom that went all the way into the early 1900s. Basically, what he thought was that there was this mushy ball of positive charge, because if atoms had negative charges, but overall they were neutral, they must also have positive charge. And then these little tiny negative electrons that he had discovered floating about inside of it. So sort of like a big spread out cloud of positive charge with itty bitty tiny little negative electrons inside. All right, so about 10 years after Thomson's discoveries, another scientist by the name of Ernest Rutherford went ahead and what he did is he shot alpha particles. Now, alpha particles are very heavy and positively charged. And he shot them at a very, very thin sheet of gold foil and observed the pattern of the scatter of particles. All right, so he knew that these heavy positive particles were basically being shot at atoms in the gold foil. And if atoms were like the plum pudding model that Thomson had put out, sort of a cloud of diffuse positive charge and itty-bitty, very light negative charges within it, basically if I'm shooting these very heavy positive things at it, he thinks it's just basically going to blow right through. I mean, there's nothing that's misty, whatever else, but we're talking about things on a small level. So he's pretty sure these particles are going to blow right through. And he starts to make some observations that then make him question that. And what he discovers is that, indeed, most of the particles do go straight through. But every once in a while, one deflects off at a pretty severe angle. And about once every 20,000 times, one comes almost firing back. And he said this was as if you were firing a cannonball at a piece of tissue and it came bouncing back. This was basically the idea that so some particles were deflected at large angles, so there's no way that Thomson's model could be correct. And so Rutherford sat down and he thought, what in the world could cause something that's heavy and positive to bounce back? And what he came up with was this idea that the positive charge wasn't spread out all over in the atom. It was in fact in a very small, dense, positive place that he called the nucleus. And then the electrons were located around that. So almost all the mass and all the positive charge is in the middle, and the electrons are very tiny and they're all the way around. So that means that most of the atom is empty space. It's nothing, right? Just a lot of empty space, but those electrons are moving around so fast and there's so many attractions going on that we don't ever see it as nothing. We see it as creating the matter all around us. In terms of other subatomic particles, the positive nucleus was actually discovered to be made of smaller positive particles that became known as protons. That was about 10 years after the gold foil experiment. And then the last type of subatomic particle is called a neutron, and that was discovered by James Chadwick in 1932. So we're going to take a few minutes here, and we're going to go ahead and watch a quick video in which my friend Tyler tells you all about the discovery of the neutron. Because it's a pretty interesting story. Kind of a cool experiment. I like it.
When we talk about atoms nowadays, we usually use diagrams like this, where we've got a nucleus in the middle of the atom that has protons and neutrons, and then there are electrons around the outside of the atom. But of course, we didn't always know that atoms looked like this. Scientists had to discover each one of the subatomic particles one by one. Because, of course, the atom is so tiny that you can't just look at one and see what it looks like. Scientists had to do a whole variety of experiments to discover these various particles, as well as the overall structure and shape of the atom. So the neutron here was the last of the subatomic particles to be discovered, and we're going to talk about how it was discovered in this video. So, in the early 1900s, around 1910, 1920, this is what scientists thought the atom looked like. It's not too different from this version over here, except that there aren't any neutrons in the nucleus. Rutherford's gold foil experiment indicated that there were protons, positively charged particles, in a nucleus in the center of the atom. And then other work by Bohr and certain other scientists gave the idea that there were electrons spinning around on the outside of the atom. but no neutrons had been discovered yet. Now, there were a few clues that led some of the scientists to think that something like neutrons might exist in the nucleus of the atom. First of all, some scientists said, look at this. There are all these protons in the nucleus of the atom. Protons are positively charged and, like things, repel, right? You've got two positively charged things, they want to push away from each other. So they thought maybe there is something else in the nucleus of the atom that helps keep these positively charged particles together, keeps them from just pushing away and repelling each other. And it turns out that is exactly what neutrons do. So that was one clue that neutrons might exist in the atom. Here's another. When scientists compared the masses of helium and hydrogen, they found some interesting things. Scientists knew that each hydrogen atom had one proton. Here, I've drawn them here. And they knew that each helium atom had two protons. They're the two protons. They decided that a proton should weigh 1 AMU, so they would think that two protons here would weigh 2 AMUs, and the two protons from here should weigh 2 AMUs. So 2 AMUs on both sides of the scale. But it turned out that one helium atom was still heavier than 2 atoms of hydrogen. And this didn't make sense because they knew that there was an equal number of protons. It turned out that it took 4 hydrogen atoms to balance out 1 helium atom. And this didn't make sense because here you've got 4 protons and only 2 protons over here. How are these things balancing out? Now, of course, you may already know the answer, although scientists back in the 1910s, 1920s didn't. And the answer is that helium doesn't just have protons in its nucleus. Many helium atoms have 2 protons and 2 neutrons. So instead of just having 2 protons, this helium atom has 2 protons, 2 neutrons. Now we have 4 particles that balance out the mass of the 4 protons on this side of the scale. So that's why it turned out that 1 helium had to be balanced out in weight by 4 hydrogens. But of course, scientists didn't yet know that neutrons existed. And here was one other thing that they also noticed. They could measure the atomic number of atoms, which is the number of protons in them. And again, they decided that each proton weighed 1 AMU. But then when they determined the mass of the whole atom, they'd find that it was greater than the number of protons. So here in helium has an atomic number of 2 protons, but its mass is 4 AMU. Where's that extra mass coming from? Lithium has 3 protons, but its mass is 7, 4 and 9, 5 and 11. So it became clear that there was something else in the nucleus that had mass and was causing the atoms to weigh more than you might expect based only on the number of protons. But it wasn't until a scientist by the name of James Chadwick came along in 1932 and he really figured out exactly what neutrons were. Here's how he did it. He took atoms of beryllium or boron or lithium and shot alpha particles at them, kind of the same way that Rutherford shot alpha particles at the gold foil in his gold foil experiment. So James Chadwick shoots these atoms with alpha particles, and he notices that rays get released from the atoms of beryllium, boron, or lithium. So something is getting shot out of these guys when they're hit by alpha particles. Now, it's not clear what's coming out, but one thing is for sure. Whatever is getting kicked out of these atoms, it doesn't have a charge. So it can't be protons that are getting shot out because they're positively charged, and it can't be electrons that are getting shot out of these atoms because they're negatively charged. So something that doesn't have a charge is getting shot out of beryllium, boron, or lithium atoms when they get hit by alpha particles. Okay, they still don't know what it is. But here's a second part of the experiment. James Chadwick and his co-workers put paraffin, which is just a fancy word for wax, like the kind of wax in a candle. They put a little sample of paraffin in front of these rays that are shooting out of these atoms. And they discover that when the paraffin gets hit by these rays, protons come, bam, they come shooting out of the paraffin. They come shooting out, and these protons get shot out really fast. So whatever is coming out of the beryllium, boron, or lithium is moving fast enough and is heavy enough to bang into the atoms of the atoms that are in the paraffin and kick out the protons. I want you to think of the protons kind of like pool balls. They're pool balls that are getting shot out of the paraffin, okay? And so at first they think maybe what's coming out of these atoms is something called gamma rays, which are made up of particles that are incredibly tiny and incredibly light. But the more they think about it, it doesn't make sense. And here's why. Because these pool balls, these protons, are getting shot out of the paraffin so quickly that it just wouldn't work if they're getting hit by gamma rays. Because the gamma rays are so tiny, it's like hitting a pool ball with a tiny BB and expecting it to fly away. Almost no matter how fast you hit this pool ball with a BB, you wouldn't be able to get it moving just because that BB is so light. Doesn't matter how fast it's going, it's just too light to be able to slam into the pool ball and get it shooting off. So they realized, no, it can't be something light. It can't be something like gamma rays. Instead, think about this pool ball analogy. If you want to get this pool ball really shooting fast, you got to hit it with something that's about the same weight as this. You can hit it with another pool ball going pretty fast, and that'll make it shoot off. So what they decide is that whatever is coming out of these atoms has to be about the same mass as the protons that are getting shot out of the paraffin. They know that the things that are getting shot out of these atoms don't have a charge, and they know that they have to be about the same size and mass as the protons. So this is how the neutron is discovered. It's neutrons here that are getting shot out of these atoms. You hit beryllium, boron, or lithium with alpha particles, neutrons come shooting out. They don't have a charge, so you get these rays of neutrons shooting out, and the neutrons then hit the atoms that make up the paraffin. They smash into the atoms that make up the paraffin, and then the protons come shooting out nice and fast because they've been hit with something that's just about the same mass as they are. So it really gets them moving. So that is how the neutron was discovered, and that then completed the idea of the atom as being made up of three subatomic particles: electrons, protons, and neutrons.
All right, so from all of that, we end up with knowledge of three subatomic particles that make up atoms. That'd be the proton, the neutron, and the electron. Protons and electrons are the only particles that have a charge. Protons are positive, electrons are negative, neutrons have no charge. Protons and neutrons are essentially the same mass. They have a mass right around a unit that we refer to as 1 AMU. You'll notice that the mass of electrons are so small that we ignore them. They're like 2,000 times smaller than the protons or the electrons in terms of mass. When we talk about elements, we almost always are using their chemical symbol. The symbol is just the one or two letters that represent the elements that you can find on the periodic table. All atoms of the same element have the same number of protons, so protons define what element it is. That number of protons for a particular element is referred to as its atomic number. The mass of an atom in atomic mass units is defined as the number of protons and the number of neutrons in an atom. Okay, so from that information, we can come up with a symbol of an element. This is called an isotopic symbol that we'll talk about in just a second. And basically, you have the symbol of the element, the atomic number on the bottom, the mass number on the top. When we talk about atoms of elements can be different by having different number of protons. If that's the case, we refer to them as different elements. Sometimes they can also have different numbers of neutrons. And if that's the case, that means that they have a different mass, but they're still the same element. We refer to those as isotopes. So you can see 4 different representations of carbon isotopes here. Carbon with a mass of 11, carbon with a mass of 12, carbon with a mass of 13, carbon with a mass of 14. They all have 6 protons, making them carbon, but they have a different number of neutrons, which causes them to have different masses. You might wonder how we can figure out the masses of atoms, and it turns out that they can be measured with great accuracy using something called a mass spectrometer. In the next couple days, you will learn a whole lot about mass spectrometry that you didn't know before, and I'm sure we'll find oh so exciting. All right, we said that the mass number for an atom is the number of protons plus neutrons in that atom. But in the real world, we have large amounts of atoms and molecules. And so as a result of that, you have lots of different isotopes of different elements going on. And so as a result, when we're doing calculations, we use average mass because that's more representative of the sample that we have. And average mass is calculated from the masses of the isotopes of an element weighted by their relative abundances. So in the end, average mass is a weighted average. All right, so this brings us then to our organization system for the elements, and that is known as the periodic table. The periodic table is a systematic catalog. Elements are arranged in order of atomic number going up. As we go down across the rows, the atomic number goes up and up and up, the number of protons. So the rows on the periodic table are known as periods. Columns are known as groups. Okay. So how do we know when to end and start as we're going across the periodic table? 11, 10, 12, 13, 14, 15, 16, 17, 18. How do we know to go to 19 and not just keep going? Well, it turns out that elements in the same group have similar chemical properties. So once we see properties repeat, we bring the element back over and we start doing it across the way again. All right. So again, as we go across on the periodic table, we're changing atomic number. As we go up and down, we have similar properties. The fact that the properties repeat on a regular basis is known as periodicity. And some of our groups have properties that are so regular or so like each other that they actually have names. The elements in group 1 are called the alkali metals. Group 2, alkaline earth metals. If you move farther over to the group that starts with oxygen, they are known as the chalcogens. The next one over is the halogens, and the farthest right column on the periodic table are known as the noble gases. In general, nonmetals are on the right side of the periodic table, with the exception of hydrogen. Metalloids border the stair-step line. Okay. And so they just sort of sit there. Stair-step line in general is our divider between metals and nonmetals. And metals are over here on the left side of the chart. One other way that atoms can be different is by gaining or losing electrons. So we said if we gain or lose protons, we change what kind of element it is. If we gain or lose neutrons, we change the mass and create different isotopes. If we change the number of electrons by losing or gaining electrons, the element becomes an ion. The atom becomes an ion. Okay? Cations, meow. Yes, cations are positive and are formed by the elements on the left side of the periodic chart. Anions are negative and are formed by elements on the right side of the chart. So you'll see the positives here, and you'll see the negatives over here. We can use the location to predict the charge of some of our ions. In this first column, we have all +1 ions, +2 ions in the second column, +3 ions in the third column, -3 in the fourth column, -2 in the fifth, -1 in the sixth, and no charge at all in those noble gases because they don't tend to react at all. We also have another kind of ions that are called polyatomic ions. These are complex ions that form from multiple different atoms. And so on your ions that you're memorizing memorizing both monatomic or regular ions as well as these polyatomic ions. Here's a list of the common cations, a list of some common anions. Again, all ions that you'll be learning the names of and the formulas of over the course of the next week or so. That's it for this set of notes.